In this example, you're asked to find the dimension of each vector space. And this is where we're assuming that we are using the usual operations of addition and scalar multiplication. So we're not going to do any kind of fancy creative definition for either of those operations. So the way you find the dimension of a vector space is find the number of elements in a basis for that space. So taking R4 as a first example, if we want to find the dimension of R4, then we need to find a basis for R4. And then the number of elements in that basis will be the dimension. You may have a sense that the dimension of R4 is 4, and you're right. But the way to show that would be, okay, we want to find a basis for R4. Let's think about what a generic element of R4 would look like. So that would be a vector with 4 entries. Let's say I call them A, B, C, D. See how that's showing up. So any vector in R4 I could break down as this vector A, 0, 0, 0 plus 0, B, 0, 0. This looks a lot like when we're finding a spanning set, or further back when you're writing the parametric form for the solution set to a homogeneous system of equations, if you remember that back in chapter 1. But anyway, this process might seem familiar to you, that's what I'm saying. So if I break it down as, into these unit vectors, or these vectors in each component where everything else is 0, and then here I could factor out A. So this is A times 1, 0, 0, 0. And this would be the standard basis for R4, would be to just list the unit vectors in each direction, which is what this is going to amount to, because now I can factor B out of this vector, and that'll be B times 0, 1, 0, 0, and then C times 0, 0, 1, 0, okay, and then D times 0, 0, 0, 1. Is that on the screen? Yes. Okay. So here's 4 vectors that span the vector space R4, because we can see that any vector A, B, C, D, no matter what these entries are, can be written as a linear combination. That's what we've expressed here. Linear combination of these 4 vectors. And when you list them, they are linearly independent. None of these vectors is a linear combination of the others. I mean, if you want to form a matrix, if you're a creature of habit in that way, then imagine that the columns are, here's your first column, here's your second column, third and fourth. It's already in the reduced echelon form. And we can already see that we'll have a pivot in every column, if you buy that. So this collection, I'll list it out here, is a basis for R4 0, 0, 1, 0, 0, 0, 0, 1. So this is a basis. Since it has 4 elements, then that proves that the dimension of R4 is 4. And I'm going to erase this, and I'll show you the notation for how we can summarize that. Get rid of all this. So now we can say that the dimension of R4 is 4, based on that basis that we found. Okay, how about P2? So we want a standard basis now for P2. Well, any polynomial in P2, so that's a polynomial degree 2 or lower, can be written as some number A times t squared plus some number B times t to the first plus some constant term C. So look, inspecting what I wrote here, any polynomial in P2 can be written as a linear combination of the polynomials t squared, t, and 1, if we picture this as c times 1, where a, b, and c can be any number. So anything in P2 can be written as a linear combination of these 3 polynomials. And this is your standard basis for P2. So because P2 has a basis with 3 entries, then the dimension of P2 is 3, because there's 3 elements in this basis. Okay. So last one, set of all 2 by 3 matrices, M2 by 3. This I don't know if I'm going to write this out completely, but so we're talking about any matrix of the form, it's got 2 rows, 3 columns. So A, B, C, D, E, F. Which, if I want to write sort of the parametric form for that set of matrices, if you guys are willing, I'm going to jump right to this. So that's A times 1, 0, 0, 0, 0, 0, plus B times 0, 1, 0, 0, 0, 0, and then you get the idea here. But I guess I will write this out. Well, here, let me do a dot, dot, dot here. So a basis for M2 by 3 would be the collection 1, 0, 0, 0, 0, 0. Is that okay? And then 0, 1, 0, 0, 0, 0. And then 0, 0, 1. Because it would have been this matrix, it would have been C times this matrix, plus D times this matrix, plus E times this matrix, and then F times this last one. So because a basis for M2 by 3 has 1, 2, 3, 4, 5, 6 elements in it. This is just one basis, but then every basis for M2 by 3 must have 6 elements. And we can say that the dimension of M2 by 3, the collection of all 2 by 3 matrices, is 6, because we have a basis with 6 elements.